Okay, hello everybody. So, this is Junichiro Horikawa, and this is a live stream called Houdini Algorithmic Live. This is a Houdini tutorial live, and which shows you a process of algorithmic design examples, the process I found out throughout my work or projects. And today's topic for Houdini's tutorial is to try to implement the so-called optimal transport, which I've have heard from one of the users, one of the people, one of the person on the chat last week. That was the first time I heard about it, but I found it really interesting, and found out there are tons of papers about this optimal transport to be used for a 3D geometries, like for morphing. So that's what I would like to talk about or tell you how to do today. Okay, so the result will be something like this. You'll be able to give an input as a geometry and morph between different geometries. There are several limitations to this process. Is that the topology has to be the same, meaning there should be no hole like a torus shape. So meaning that the surface has to be a genus 0, but besides that, it works pretty fine. And one of the limitation also is that I am using a library, external library for the spherical parameterization, one of the steps for this process, because I couldn't have a time to implement myself. So that's going to be my homework to try to implement this spherical parameterization itself. But for today, I'm just going to use the open source software that's been provided by the author of one of the paper that I found out, which is still great because it's open source and in a BSD license, so you can also ship it for commercial work. Okay, so the paper that I read is this one by Michael Kasdan, Jake Solomon, and Mira Ben Chen. Can mean curvature flow be modified to be non-singular, which tells you how you could minimize the energy on the shape to create a sphere ball like these. Also, a paper by Alex Baton, Keenan Crane, and Misha Kasdan for orienting the spherically parameterized geometry to orient the shape to match the original shape or original geometry. So based on these two papers, Kasdan, I think, provided an open source software called Morph registration on a GitHub. So that's great because we can see the source code from it and see what is all about this paper. And we can also use the binary software, a binary code from here to for a process. And what's good about this again is that it's a command line based application, so you can call the software externally from Houdini using Python and flawlessly retrieve the spherical parameterized mesh using this software from Houdini. So that's good. So that's great. So, but the limitation is that it is only available for Windows or Linux. So if you're using Macintosh, I think you can't use this, I think. So that's the limitation. So if you want to use the Macintosh, you have to build it by yourself, these C++ source code, or have to implement the parameterization by yourself, which I would like to do it in the future as a homework, but not today because I didn't have much time. So the link to this GitHub page is already in the YouTube video description page, so you can go from there. If you go to the video description page of this YouTube live stream, I have created the reference link to this GitHub page, so you can go there. Okay. Now, since if I try to paste the link to chat, it just deletes automatically. Maybe YouTube doesn't really like having links on a chat. Okay. So, what was I? So first thing first, you have to download the executables. But the problem, as you can see, from GitHub, the link is already dead. So in order to download the executables or DLLs, you have to go to this home, which is the home for Mikhail Mishikastan. You can go to this code and executables, and there's a page for Movius registration, and you will be able to see the same link here. From here you can download the files, so you can just download two links under binaries. One is Windows executables, one is Windows libraries and DLLs. Okay. Now, if you have downloaded, you'll have a zip file like these. So just extract it anywhere. I'm just gonna extract it here, and this one as well. Okay. Now, what I need to do now is to gather all the exe file and DLL in the same folder. So I'm just gonna copy this to this root folder, as well as these DLLs. I think .lib is for the the Linux. So you might only need DLLs if you're using Windows. Alright. I'm just gonna delete those folders. Now I am ready with the softwares. You might want to check if it opens up by double clicking it, and it says it's been protected by a PC, but you can just run it even though it is from unknown source. This means run. Okay, so just do this for every software. Nothing happens because this is a command line based application, but still works. Alright, there you go. Okay, hi Kitma. Have you explored using ChatGPT to assist in writing Vex? It's quite amazing. I did use ChatGPT, especially to understand the term for mathematical terms. I didn't use it to assist my Vex, but I did use it for Python code a lot. Yeah, I found it really useful. Sometimes it just generate a fake library, which is sometimes not usable, but most of the time it's pretty amazing. Yep. What was I? So I have just extracted all the files, and let me create a new file for Houdini and save it on the same directly as these DXS, so that'll be easy to access. So I'm just gonna save this new file under the Houdini, what was it? Right here. Okay, and I'm going to name this optimal transport. There you go. Okay, now first thing first, let's try to use these DLLs without using Houdini for now, as it is for now, and see how this works. Okay, so there's 3 exif file. One is parameterization, one is register, and one is sphere map. So let's see what each one does, and you can check that by going into this web page or GitHub page. And there's a section for each exif file executables, what these does. So sphere map computes the conformal parameterization of watertight. Genus 0, this is what I was talking about. Genus 0 surface is the one that doesn't have any like holes, like torus or donut. To the sphere using conformal mean curvature flow. Canonically, considers the parameterization relative to Mobius inversions, generally the low frequency spherical harmonics. Okay, so I think this is the one that we want to use in order to create a spherical map. Now, I think I didn't really tell you the reason why I need this spherical parameterization in order to do the morphing. Okay, so the key idea here is that once you have a geometry you want to morph between, let me show up the edges. So for example, let's say you want to morph between these pig head and this rubber toy. Topologically, it's the same genus 0, but the thing is it has different UVs, different vertex positions. For example, this one has some branches as a leg or on the head. The pig head has some like mouth space here and so on. So most of the time it's a bit pretty hard quest to morph between these two geometries by keeping the vertex, the original vertex as it is. But there is a way to transport from one geometry to another geometry, and seems like there are several ways to do that, and one of the way is to use a spherical so-called spherical parameterizations as a medium. Spherical parameterization means you first map this geometry onto a sphere, and which looks like this one. So by somehow converting this geometry, pushing each vertex to lay on top of the sphere, you could create a sphere. As long as you don't have any holes like torus, any geometry which has a genus 0 surface can be mapped on a sphere like this. So for human head, looks like these, which might have a hole because this is an open surface, I guess. And for the rubber toy, you could map it like these. So by mapping the geometry to a sphere, each sphere can now be compared to each other like these. So from this sphere to this sphere, it can actually sample the position to each other. Okay, meaning it'll be able to gather a positional information at this point on the human head, which corresponds to the peg head position corresponds to where it is here. And by defrosting the spherical position back to the original geometry, you can actually transport the position itself. Using the same idea, it can be used to transport any attributes like UVs, colors, anything. Okay, so the idea itself is pretty interesting, and seems like this spherical parameterization can be used for many purposes, not just for the morphing, but texturing, analysis, and so on. So I think try to use this as an example will be a great start to see its usage. Yeah. Okay. Yeah, the main topic for today is to do the morphing, but it can be go further using the same technique, I guess. That's what I wanted to show. So that's the key topic. So that's why we need to do the spherical parameterization. The spherical parameterization itself do need a little bit of nonlinear optimization based on this paper, so I wasn't able to finish understanding it, how to implement it, so maybe that's for my homework. So today I'm just going to use the software they have provided on top of Houdini. Okay, so let's try to use the software, the command line software, how we see how we can use these softwares: parameterization, registral, sphere map. And as I said, maybe the sphere map is the one that we want to use. The parameterization says replaces position. Okay, so this is just to replace the original geometries vertices into a sphere, so might not be necessary to use. Register performs fast spherical collision, aligns rotational component reviews. I think for this one, this has already been done here. This is probably the independent software to do the Mobius inversions. So just gonna use this sphere map as a software, and if you open up this accordion, you'll able to see what kind of command you can use. So first you have an input argument, and there's an output argument, output T, output G, mesh, fill, blah blah blah, and all sorts of parameters you can set. But for now I'm just going to use the most simple parameters, the input and the output. Okay, and output will give you an additional attribute called px, py, pz, which corresponds to a spherical coordinate. So I think that's the things that we need to have. Okay, so in and out. Let's try to use this. So in order to use this, you need to use the command line. So open up the command prompt on Windows. And in order to use this, you need to have an input geometry in PLY format. So let's just create one sample PLY geometry from Houdini. I'm just going to use a pig head, right? Then, probably it needs to be triangulated. So just going to use a divide node to triangulate the geometry, then I'll put this file as a PLY file. So let's just name this pig head PLY. Right, save. We'll save the file to under a geo. So this is the one. Okay, now in order to use the spheremap.exe file. First open up the command prompt, drag and drop this spheremap.exe space, and now you can enter a argument. For example, the first argument is the input, so you need a -- n space the name of the files, which is this peghead ply that I have just exported. So I'm just going to drag and drop it. And now you also need the output to get the result. So it could be any name in ply format. So I'm just going to say result.ply. Alright, and enter. It will run on a background, and you will able to get the geometry somewhere. Okay, I started on my user folder, so I think it's in the user folder. I think I need to change the current directory to somewhere around here. So I'm just going to change the directly to this folder. Yeah, using cd, then call the same command again. Okay, now do I see it? Wait, the directly didn't really change. Maybe I need to change the drive itself. I forgot how I can change the drive. Am I not able to change the... Nope. Okay. Now it's... maybe not. Okay, I'll just try it on the C drive then. Then in that case, I'm just going to... let's see. Just going to create a folder on the desktop. I'm gonna call this morphing and just change directly to this morphing. Okay, now it changed. Now I'm just gonna call the same command again. This one. Right, then inside the morphing, the new file is being created called result.ply. Right, like that. Good. Now, this is, let's try to open this file and see how it looks like. Just gonna copy back to here, maybe under a geo folder, and see how it looks like. So I'm just going to open it up using file node under geo result. Okay, so let's check how it looks like. So you have colors on vertices. Let's also check the geometry spreadsheet. So you have new color attributes, new px, py, pz, which is going to be the spherical coordinate for each vertex. The UV has been removed. No primitive attributes. Okay, so this is all we have here as an information. If you want to keep the original UV somehow, then you can still do that by attribute transfer. Since the mesh structure hasn't changed, the number of points or number of triangles didn't really change, so you can just transfer the UVs from vertex attributes like that if you need it, though I don't think I need it. Okay, so what I would like to do now is to see how this px, py, pz is working. So let's try to update each vertex positions with these px, py, pz. Okay, using point wrangle, I'm going to create a vector value from the attribute. See how it looks like, and now you can see the sphere has been made from an input geometry. Cool. Okay. Now let's also try to export another geometry to test the simple morphing manually for now. Later I'm going to make it a bit more automatic, procedural, by calling the command line application from Houdini. But for now, let's try to do this manually to understand the workflow. Okay, so for the rubber toy, again, I'm going to export the geometry. Rubber toy, export it. Okay, which will give a geometry right here. All right, now let's try to create a spherical result from this rubber toy as well. I'm gonna rename this result to big head result and open up the command line and try to do the same process. Okay, so first, spherical map, space, in argument. We want to change this rubber toy as an output. I'm just gonna paste here and rename this to rubber toy. Okay, and enter. Update failed. Factorize matrix numerical issue. Okay, now I see some problem here. Oh, hello, Raphael. Oh, thanks for the super chat. I've been watching you. Thank you so much for online workshop. Online workshop. If there's any need, maybe that might be fun. Thank you for the comments. Okay, what was I? So the problem with this rubber toy is that it has multiple number of unconnected geometries. If you double click on the rubber toy here, you can see that this is all unconnected. So in order to use the spherical parameterization, geometry has to be connected as one whole piece. Cannot be separated like these. So I'm going to merge these together by using Boolean for now. Using union. And now everything has been connected to as one piece. Let's export this and run the command again. Okay, now I think it has successfully created the result now. Alright, let's load that geometry. So first, let's change this name to pickhead result. Just gonna copy one more. And for this one, I'm going to load rubber toy result. Okay. And if I change the position of each vertex with the pxbypz, it also creates a sphere map of a radius of equal to 1. Okay, so now we have two spheres and we can use these to actually create a morphing at this point. Now it might not be a clean morphing at this point because the number of vertex is different on each side, especially on the rubber toy that has like number of 10,000 but this one has much less points. So we could imagine that there is some resolutional gap between these two geometries, but let's see what happens. I'm just going to show you the base idea how you can move between geometries. So using point wrangle, I'm gonna make this morph test. Okay, so from here to here, you want to gather the information from this vertex, which is coming from a peg head, and for each point you want to check the corresponding positions attributes. Any attributes is fine. This time we want to check the original position attributes, and currently we don't have that. If we look at the attributes, we don't have the original positions, which is these peg head point positions. So we're going to create that by using rest attributes like that. All right, and then we can we can sample these rest attributes at the corresponding point position on a sphere. Okay, let's try to do that. So the target rest position can be retrieved by using UV sample from a second input. And what we want to have is the rest point position, and in order to sample the position we can just use the P itself, because P is on the sphere. P's length is always equal to 0, always equal to 1, so it's pretty similar to a normal directional vector value. Okay, so you can also use normal if you have a normal on top of a sphere, but anyway, this is fine. And now finally the on point position as a sampling source. Okay, so that's the target rest, and the source rest position is just its own attribute, so you can just write it like this. Now you can now move between these two geometries by using something like lerp between the source rest and target rest, and having some kind of parameters. So initially it's a peg head, and by moving this t value you can change to a rabbit toy. As you can see, because the number of vertex is different on each side, the one you got on the target side will have a less detailed part, especially on the legs and the head. So later we're gonna fix this as well, but for now I just wanted to show the basic workflow, how you can move between different objects. Okay, so now we have confirmed the most easy way to move between geometries. It's time to make it a bit more efficient. We don't want to go back and forth to the command line each time we change the geometry. We want to call this automatically from software, from Houdini. So that's what I'm gonna do next. Okay, calling command line application from Houdini is pretty simple. You just need to use a Python with a subprocess library. So that's what I'm gonna try to do. All right. So let's create some setup for that. Just gonna keep it as a sample for manual process, and try to bring these sample geometry to the right side. Use it as a test case. Okay, now so what I need to do first is to export this file as a PLY format, right? So let's see how we could do that using Houdini Python. Right? So if you go to a geometry section, whole geometry, and there is a one called save to file here. So we can use this function to save specific file with the file name. Okay, so let's try to use this first to export the current geometry to a PLY as a PLY format to anywhere you want. Okay, so I am going to create a Python node. Let's call this call spherical function. Okay, now first thing first, I am going to create some parameters. So first I have an executable, which is going to be the path to the exit file application, I mean, and you can just read it. Okay, next you need an input to call when you call the command line application, you need an input argument. So let's have it as an input. Okay, which is again read only. Another file. You also need an output, which is going to be outputted on some directly. So make it as write only. Okay, so these are the parameters you need for now, I think. So let's go. And let's try to read those parameters first inside Python code. So, first of all, application node. You can use a parm, and the name was executable. And since it is a string, you can evaluate it as string. Okay, rest is pretty much the same, so you're just gonna copy these. You have an input, you have an output. Input, output. Alright. Now, next, what I want to do is to, what was I trying to do? So I want to save this file so that we can use this as an input on the command line. So meaning we have to save this files with this input string here. So let's just choose any input string. Just gonna name it to how do I name this? Test input dot ply accept. Okay, as an output, I'm gonna name it as test output dot ply. All right. The exit. Oops. Spell mistake. Spell mistake. Executable for the executables, it is the path to the application, so you can just refer to this spheremap.exe. Accept. Okay. So now you have got every information. It's time to write some code to export this file and use it for a command line and retrieve the output geometry and read it on Houdini. So then let's do that all inside this Python code, right? So first thing first, let's save this geometry as a PLY format, in this case, this one. So this file. So let's see how we could do that. So if we look at this one, we can just use the geometry function save to file with the file name. Seems like that's all we need to do. So let's see if that works. Geo dot, so we have geo dot save to file input. Okay, now let's see if it run. Where is my folder? Okay, so the file has been created, so I think the exporting has successfully done. That's good. Now, after you have exported, you want to open this with the command line application. So let's write some code to execute a command line application from a Python. Now, I got a hint from a node called instant meshes. This one also does the same similar things. It also opens up executables, external executables, and run command line application. Run it as a command line application. So I'm doing the similar things using this Python node, right? So going back, first thing first, I need to have some libraries to call a command line application externally, which is called sub process. I may also need OS to specify the path, the file path. Alright, so now let's start creating the command first. So the command, I'm gonna create a command argument as a array. And the initial array will be a executable path, which is this application. So this will be the first item on the array, inside the array. Now, after this, I'm going to append all the argument we need. In this case, we were using two arguments. One is a in argument, and one is the out argument, together with these file path after the in and an out. So first we have in, then we have a input path, file path, next out argument, then output path. Right. Now all the command argument has been inside one array as a string. We want to transfer, or we want to bring this to a command line application to actually run the program. And we can do that by using subprocess.call with cmd. And that's probably all you need to do. If you do that, the command line opens up on a background, and if you look at the folder, there you go, the file has been exported. That's cool. Right, and as soon as you have exported file, you want to import it back to Houdini to reuse it, to use it on the Houdini side. So next thing we're gonna do is to load the exported file, output file, and let's see what kind of functions we can use. So there is a load from file, so I think this is the one we want to use. Okay, so geo load from file. This time we're gonna import the output. As a result, there you go. The geometry has successfully been imported back, which has all the px, py, pz informations with it. Cool. Meaning you can just replace the geometry procedurally and it just runs automatically like this. Alright, useful, isn't it? Now you can just close this command prompt, just have your Houdini window only to run this setup, as long as you have the executable path to the same directory, like that, right? Okay, I hope you found this useful. Now, having these set up, next thing I want to do is to create a clean morph transition, clean morphing animation between two of them, between multiple number of geometries. Okay, so in order to have multiple number of geometries, I don't think you can use the same file name, because each one needs to use a different file name, I think. So I'm just gonna change the name to something else for pighead and rabbit toy. Probably later I'm just gonna add another one later. So for this one, I'm gonna call this test 1. Create another Python code. And I might also want to have some toggles or something, so that it's not gonna run until I say run or something. I press button or toggles or something. Because right now it just runs every time I change some things on input or output. That might be a bit disturbing. So change this to test 2. And this one to test 2. In terms of the code itself is pretty much the same, so I'm just going to copy and paste the whole code set. Like that. Which makes sense. If you change this code, then this will also be updated. Alright. So okay, now that we have two geometries, pighead and the rabbit toy, let's also have something like cache. Let's try to create a morphing, a clean morphing. Now, previously I was using these process, so let's try to copy this one and see what we need to do in order to make a clean morphing effect without losing the detail too much. Okay, so the problem with this one is that, for example, the reg part, the leg or the head part, if you look at the part where the leg exists on the original geometry on the sphere, probably these are the leg position. You see that the mesh on a sphere is pretty small. So thing is that it's pretty hard to sample these specific positions using a low res input vertex. For example, if you look at the pig head, the resolution of these triangle mesh on a sphere is pretty low res. So even though it has detailed information on the target, you can't really get those details from this one, from the pig head, because it lacks the number of points. Okay, so the idea here is, what if we could have a sphere mesh which has all the points from the source mesh and also from the target mesh, then the resolution problem might just goes away. Meaning, if we could somehow merge these two meshes together and create a new triangular mesh between these 2 points, the points from this mesh and points from this mesh from the repertoire, and use those 2 point set to create a new sphere map and use it as a morphing source. Then each one the merged mesh has the sampling position to both to the pig head, and the rabbitoid will have more clean morphing effect. Okay, so that's the idea. So the idea is, first we get the point information from each of the geometry using anything like delete with key points. Okay, let me also make this background dark. So this is the point set from a pig head, and this is the point set from a rabbitoid. And what we want to do is to merge these 2 points together and create a new mesh from these point set, a triangulated convex mesh. Probably using a Delaunay triangulation. Okay. Please wait a little bit. My battery is running out. Okay, sorry. So how can we do that? In order to achieve a mesh out of these points on a sphere, what we could use is a so-called stereographic projection. Combined with a Delaunay triangulation. So by using stereographic projection, you can project the points on a sphere on an infinite plane, and then once we have that infinite plane, the points on an infinite plane, we can create a triangulated triangulation using Delaunay triangulations. In Houdini, we have a node called Triangulate 2D, so we can use this to create a 2D Delaunay triangulated mesh. Then after we have created that, we can wrap it back to a sphere using a rest position or something. And as a result, you'll get a wrapped, triangulated, clean mesh, having all the points as a mesh vertex. Okay, easy as that. So first thing first, what we need to do is to create, project these points on a infinite plane. And if we look at the Wikipedia here, you just pick some of the points on the sphere, something like a north pole on the top, then do the projection to the sphere, to the point on the sphere, and use those points and just use those points, which is on the infinite plane. This is the section view for that. So we just need to create the points here on the north pole, create a vector value, a vector directional value, a directional vector from the north pole to each of the point position on the sphere, then using that vector to project on a xz plane, on an infinite plane. That's all we need to do for the stereographic projection. So let's do that. I'm gonna do that using point wrangle. Right, and so let's first create a north pole vector value, and then we're gonna create a directional vector value going from north pole to each of the vertex. And each of the vertex is at P, so direction is at P minus pole. Okay. Now, all we need to do now is to project this vector from the north pole to an infinite plane. Calculate intersections. Now we could probably use intersect functions, but that's a bit too heavy, so I'm just going to do it mathematically. Okay, so in order to do that, we know the radius of this sphere already, which is 1, so it's pretty simple. You just need to multiply the length of this vector so that the y value, if the y value becomes 1, then meaning that the directional vector has been projected on the plane. Okay, because it starts from the pole. So first I'm going to calculate the current length of the current y length of this direction, which is directional y absolute, right? So that's the length of the y. Now next you want to, by dividing the direction by y, you could extend the scale so that the y becomes equal to 1, meaning the directional vector value will try to reach to the floor, to the plane, infinite plane, which is on the xy plane, xz plane. Okay, finally we can update the point position by starting from the pole and add direction. There you go, easy as that. So it has a merged point cloud together with the pig head and the rubber toy. Interesting, isn't it? Okay, so after this you can use a triangulate 2D to create a triangulated geometry out of these point set, like this. Now there is some limitation to this method related to the precision of this triangulate 2D, because there seems to be some threshold for the triangulation 2D inside. If the vertex distance is too close to each other, sometimes the mesh is not being created with this triangulate 2D, unfortunately. So if you want to have a more precise 2D triangulated 2D geometry, then you might need to again call some Python functions or something else using external functions, unless they opened up an option for 64-bit precisions for this one, but I don't think it's gonna happen because that's not the usual use case for this one, I guess. So that's the limitation, but still it works better than it works fine in most of the cases. So as soon as I created the triangulated geometry out of these plane, we can wrap this back to a sphere. And in order to do that, we need to have a original point position for these spheres. So we can have original sphere position as rest, or maybe sphere pos. Then after the triangulation, we can use that to make it back to a sphere. There you go. And as a result, it contains all the points from a peghead and the rabbitoid, which has been spherically parameterized. Now it is missing a part on the top or on the bottom a little bit, because yeah, you always are going to have some kind of a hole using this process. This is kind of a limitation, so if you want to close this, you could also use a polycap or something to close the mesh. But anyway, most of the time it works fine, I think. Alright, after doing this, I'm gonna make sure to make everything triangulated. Okay, now that I have this mesh, I can try to use this as a morphing source geometry. So I'm gonna bring this one here and make it as a first input. Now this doesn't have an information of either pighead or rubber toy anymore, so I'm going to connect the pighead information to the second input and the rubber toy to the third input. Okay, and now we also need to rewrite some of the code. So first of all, the source rest will coming from the second input, so written like this. The target is now on the third input, so something like this. And I guess that's all you need to do. Now the morphing becomes more clean. You have more details between two object morphing. The color is also mixed up, so you might also want to get rid of the color information, which comes from the normal direction, but it's not useful anymore, so you can just get rid of it. Or just create another normal based color by yourself. Like that. Okay, working great. So that's pretty much it in terms of the process. Simple as that. There is still a limitation to this method. For example, if you have a really like long leg as a geometry, or branches as a geometry, such as squab, this one has a little bit of problem because it has a long, how do I call this, tentacles or legs. And these are giving you a really small mesh on a sphere, and it is a bit hard to sample these, even with these triangulated 2D. So because of the precision issue, a lot of the details has been lost when using this triangulation. So in order to preserve the original quality, you have to change this to something more robust, more precise. Instead of this, maybe you can write your own code to do the triangulation, or use some kind of a library to do that for you. Well, let's see how it looks. So I'm gonna connect it here, see what happens. Okay, as you can see, if you have a long tentacles or a leg, you are going to have some kind of a detail issues at the point. So that's related to the precision of the triangulate 2D, unfortunately, so nothing I could do at this point. But if you fix that, it will become much clean. But anyway, it still works. Alright, so that's the limitation. Besides that, everything works just fine, I think. Alright, so today's tutorial was pretty simple because I was just using the external library as it is, so that was kind of a cheating, but hopefully you'll understand. Let me bring that as my homework, and if I understand better how the process will done for the spherical parameterization, I would like to share that with you again sometime in the future. Okay, hopefully you understand. But as a practice, this is useful, I guess, in many ways. Okay. I also had a question if you can also morph UVs. You could also morph UVs, but if you want to use the original UVs from the geometry, that is going to be a problem because each geometry's UV has some seams. How can I see like this one? So each UV mesh has its own UV seams, and it might be okay on the body side, but on the seam edges, each seam doesn't correspond to each geometry, so that's where you have some issues with some kind of errors. So instead of using the original UV, I would prefer using a different types of UV for this kind of setup. Since it is being mapped to a sphere, you can actually use a polar based UVs for these spheres. Using a UV project, you can use the polar based, which is more like a Earth like mapping UV. And by using this one, you could actually, this is pretty much the same for both this one or this one, even if you change the mesh you might have some problem on the top, but other than that, it the transition between the geometry with this UV is pretty smooth. So let's try using this one for a UV transition. So in order to use this, I would just connect it here, connect it here. Oops. To make it easy, I'm just gonna create a UV to a point. Maybe it's better on the vertex, but oh, it's not really clean on a point, so I'm just gonna make it back to vertex. Okay. So currently there is no UV, so we have to transfer the UV somehow, just like we did for the rest geometries. So to do that, since it is a vertex based attributes, it might be better if you use the vertex wrangle. Alright, so I could connect it before changing the point position, because point position is used as a samples, and connect the source and the target. Now I could copy these, and instead of using rest positions, what I want to get is the UV, and what I want to change is also a UV. And that's all. There you go. And if you look, maybe the color is a bit too busy, so let's make it constant, just seeing the UVs. See what happens. If you do the morph, okay, let's also link this parameter to here. Right? And see what happens. Okay, so as you can see, the UV is being transferred smoothly because it's both are based on the polar based UVs. Yeah. If you try to use the original UVs, then let's see what happens if you do that. So using attribute transfer, you want, after you have imported the geometry, you could get, you could transfer the attributes, vertex attributes, same for these one. Alright. Oops, the position is a bit different. Okay. There you go. So, looking like this and looking like this one. Let's see what happens if you move between these two vertex UVs. So we can just disable these and see what happens. So as you can see, there seems to be some issues on the seam, and if you change the T value, the body side looks interesting, but there is a problem with this UV seam area. So there might be a way to fix this, to have some modification on the edges on the seam side, but otherwise it's a bit unusable. Okay, which might be possible to use this for some kind of artwork in this case, but I'm not sure. So I guess I would prefer using polar-based UV, which looks a bit cleaner. Okay, there's some issues on the also on the seam. Maybe we need to fix that. Yeah, I'm not gonna go deep into that because it might take some time to fix that. But it's much better than the original UVs, I think. Okay, now now that I have all these set up, explained, let's also create some animations out of it and just finish this live stream, shall we? Also, let's create some function for the Python to do the pause and calculate, so that it's not gonna recalculate unless I force it to. Yeah, how do I do that? Let's see. Well, I could add the button, I guess. I don't know what this button will give you as a value on Python, so let me just check that. Okay. Okay, so it probably will give an integer value. That's what I assume. So let's see. Let's go back to a Houdini Python documentation and look for the parameters. Parameter. And search for eval. So yeah, it doesn't have any boolean, so maybe it will give you a integer value. So let's try to use this one, eval as int. And let's check what kind of value do I get. Oops. Non-type object has no attribute, eval as int. Non-type. Maybe the name was okay. It was named as run, not button. Still an error. Eval as int cannot evaluate this param as the desired type. Oh, okay. What happens if I do eval? Okay. So it did give something. Didn't really print out anything. Let me open up the Python shell. See what happens. If I press it, nothing happens. Okay. So maybe I need to use this to execute the Python code. Maybe using callback script or something. Yeah, probably that's what I need to do. Okay. Oh, that's forgot how to do that. So maybe I shouldn't place the button here, but somewhere else. Maybe it's a good idea to make it package as a sub network. That might take some time. So Well, let's do that, shall we? Since I have some time. Yep. Okay, so just delete these. And I'm gonna use it. I'm not gonna make it as a package. So this is an input. Probably I could also cache these input. And do you have the ZBrush? Well, I tried it previously, but I'm not really good at it. Yeah. Really, actually bad at it. Bad at sculpting. I mean, I really admire people who are really good at these sculptural works. Where shall we? Probably this will be the final output for the package, I guess. Okay, so now I have these. Let's create a sub network like that. And I am not going to make it as a HDA because it's going to be hard to share. So I'm just going to, yeah, I'm not going to create a digital asset, but I'm just going to edit these. And let's see, yeah, I could go to the type properties. Type should not normally be. Maybe I don't really need to change these, but okay. I guess I need to make it as a HDA in order to add the parameters here. So I'll let that do. I'll let it you to do that. Instead, I'm just going to add the parameter here. Okay, so we had an input app input output. We might want to have a button. Yeah, maybe. But how do I use this? Not really sure. Okay, just leave it as it is for now. Have you thought about using, in the end, if you have time, can you please tell some basics of reading these scientific papers and applying those methods to Houdini? Have you thought about using AI for Houdini algorithm? Actually, I'm not really good at reading scientific papers. I need to practice myself. I mean, I'm not from a mathematical background, so initially reading these papers is a pretty hard thing to do for me. Especially, I don't know a lot of the notation for the mathematics. So I need to read really slowly what these are about, what these energies about, what these things are about. And there are a lot of parts I don't really understand. So sometimes I just guess from the output result on a paper or some of the equations and skip some of the small details on the papers. Yeah. So I guess I'm not the right person to tell you how to read a scientific paper at all. Yeah, that's what I need to study more. I'm still in learning. I'm just a student, self-taught student. Okay, and using AI, haven't tried it myself. I mean, I did use ChatGPT to assist me in some coding, but haven't used a direct usage like Mid-Journey or something. Might be really interesting. I do see a lot of people trying that, and it all looks fascinating. So yeah, need to try that out myself as well. I mean, I would definitely want to create a machine learning setup in Houdini. It doesn't really have to be deep learning, but just a simple neural network. using it to train some of the geometrical operations to fasten the process, some of the process. That might be really cool. Yeah, maybe that's what I would like to try out in terms of AI with Houdini. Okay, what was I? Copy parameter. Paste it here. Paste it here. And here. Okay, what else? I guess I'll also would like to think about how I could use a button or toggle to run the program. Maybe toggle might make sense for me because it's a bit easier to control. So I'm gonna use a toggle to run. Yep, and use this to switch whether I want to use this one or not. Okay, so switch with run, and if it's not running, maybe I can just open the file from an output. This one. Otherwise, you can output these. Or maybe, wait. The output is coming from here. So I think I need to switch it here. Right. Yeah, this is what I need to do, I guess. How's that? I think that makes sense. If I use run, it just use the Python code. Yep. If not, you can just use the already cached geometry as a file, which is this one. Yeah, guess makes sense. Maybe. I don't know. Okay. So I can name this to spherical parameterization. Let's copy this to replace this one. Probably I should also have this divide node inside. So I'll just bring it here. Because we want to make sure that the geometry is triangulated. Because the program only accepts the triangulated geometry, I think. Okay, now let's change the name to test2 test 2. I'll connect this one, run it. All right. And the rest can be done like this. Okay, now we can delete these. And that's more safer. Unless the run is toggle run is off, the Python code is not gonna run anymore. Just gonna use the cache geometry. Cool. Alright, and going back to the final result. What else what we could do? So yeah, I was about to show how you could create animation, right? Well, in this case, I'm just having one sliders controlling from one object to another object. If you want to move between multiple number of objects, then you could also do that. Let's give a human head. Oops, not head. Test template head. Give another spherical parameterization. Name this test 3. Run it. There you go. Okay, now you could pretty much do the same thing for this one. First, you could create a UV, polar-based UV. Now, if you want to morph between like more than 3, like 4, 5, 6, and right now I'm using the input for the wrangle to control the morphing, so it could run the maximum of 3 objects in terms of the morphing, but if it goes up to 4 or 5 or 6, then you need more inputs. So we need to think about some other way to create the setup, I guess. So in that case, maybe we could do some other way to do that. And we also want to add the points from this human head as a final geometry. So we could retrieve the points from a human head and add it to the merge. Will create a new mesh which contains also a human head point position as a sphere. Nice. Okay, so to move between multiple number of objects, we could use maybe a switch node. One for the source switch, one for the target switch. Based on some conditions. Okay, so let's create a null node to have the global parameters just like the morphing parameter, like the time-based parameter. Let's see, I'm going to say, I'll call this morphing t, stands for a time, go from 0 to 1, and based on this information I want to move between multiple number of objects. Okay, and let's also define how many objects you want to use in terms of the morphing. So num objects starting from 2, because you need to have at least source and target. Okay, so let's say we want to have 3 objects for now. Copy that. And for the morphing target, I'm gonna make this as a time-based value. So I'm gonna create an expression ff divided by f, and we'll create a value between 0 to 1. Like that. Okay, I'm gonna copy this parameter and somehow use it for a source switch and target switch together with this number of objects. Okay, so if you have 3 objects, then for first 33% of the timeline, you want to make the source switch to bring 0, which in this case, wait, this is sphere, right? So 1, 2, 3, 1, 2, 3. So the first 33%, we want to use this one for the source switch, and this one for the target switch. And the next 33%, we want to use this one for the source, and this one for the target. And last 33%, we want to use this one for the source, and go back to the first one, goes to the target. Okay, so let's create some kind of some expression for that. Right, first copy the morphing t, which goes from 0 to 1. Now we could then multiply this by a number of objects, right? Which will give you a float value between 0 to 3. Now I want to make it as an integer because we're using it on the switch node. So we're gonna use the floor, and let's see how the number changes by changing the timeline. So 1, 2, 3. We don't want to go till the 3. So once it comes to 3, we want to make it back to 0. So calculate the modulus, calculate the remains with the number of objects. So as a result, 0, 1, 2, 0. Okay, that's good. So that's for the source switch. Let's do the similar stuff on the target. So what we need to change here is changing this floor. After we have made a floor value, which is this integer, we can then add by 1. Then make a parenthesis like that, and see what happens. So let's check. So starting from 1, 2, 3, no, 1, 2, 0, 1. Okay, so it looks good. This one also looks good. So the switching part is now okay. We can now use these to the morph and connect this to the source and the target for this one, and to the UVs as well. Now next things we want to do is to modify these t-value here in order to do the morphing. We cannot just bring this value itself as it is, because the first morphing happens from 0 to 33%. So what we could do, again, we could multiply this value by 3, and then we could calculate that we could get the remains when divided by 1, which will give you a value between 0 to 1. So meaning, I'm gonna create another expression, morphing t multiplied by a number of object, that will give you a value between 0 to 3 in float. But then what we want is the value between 0 to 1, so going to calculate the modulus remains when divided by 1. Now let's see what happens. First goes from pig head to rubber toy, and rubber toy to human head. Okay, human head is a bit too small. Let's change the size, but it seems like it's working fine. So a pig head is like this size, rubber toy, maybe move this to a somewhere close. Yep. Rubber toy, maybe make this a little bit bigger. Human head, where is it? Where are you? Okay, there you go. Make this a similar size. Okay, we have to run the parameterization again for each one, since we have moved the position. I mean, might not need to do that, because just changing the position doesn't affect the parameterization, so it might not be necessary to do this. Anyway, okay, so now okay, I think the cache is not being used correctly. Huh, seems like we need to do the reload geometry once I click this run. I see. Alright, then we might need some expression for that. Once I click run, some kind of a call script must also run in order to reload the file geometry. Right. Okay, let's do that then. I'm gonna save this. I'm gonna know how I could do that. First of all, I need to find out the node position, which is called file1. Okay. I guess I could do that using Python. So, node. I need to go inside a node, so how do I do that? I guess I need to look for the Python documentation. Actually, what I need to know is the parm, so parameters, so dot be inside the node and wonder if this could work. And it's called file1, and the parameter name is, what is it? Reload. Reload. And eval. Not sure this works. Let's see. Okay, let me make sure I save this, because sometimes it gives you an error. Run it. Okay, it's not doing things that I want. What I want to have is the reload. Yeah, it's not running. So probably I'm making a mistake here. Okay, okay, not eval, but I guess there is a function called press button for the param. Yeah, this one. I guess I need to use this. Let's see. Okay, let's try this again. I need to change the shape in order to see the changes, so I'm gonna make this back to 0. Right. If I turn this off. Not sure it's working. Let's make this back to 1. Okay, and let's run it. Okay, and if I turn this off and if I see the same geometry, I get success. Okay, looks good. Looks good. So it's working. I think it has worked fine. Now I want to do the same thing for every other parameterized stuff. So I'm just gonna copy these, paste it here. Paste it here. Okay. Sounds good. So now everything must have been updated. You can now have more better size morphing. Cool. All right. And you can have infinite number of morphing in this setup, I guess. You just need to add an input to these two switch and change the number here. Yeah, that's all. That's all you need. If you want to add one more, let's add Tommy. This one is not connected, so I think I need to do the boolean if it works. Maybe this is just a surface, so this might have some problem even with the boolean, but let's see. Boolean union. Okay, seems like everything is connected. Let's copy another spherical parameterization. Let's change this to test 4. Test 4. Connected. Run it. Okay, I think it's running. It's a bit slow. Okay. Did I get any output anywhere? Nope. If I didn't get any output, maybe I am getting some errors with the result. Okay, so this is the result. If I look at the parameter, okay, it says px, py, pz is none. So meaning it couldn't make a sphere. So probably there are some connection and issues with this geometry. So in those cases, I guess I need to make it from BDB. BDB from polygon. Convert it back to meshes. Like that. The detail has been lost. So that's the limitation with the library that I'm using, I guess. Has to be really clean geometry for the input. So maybe that's one purpose we need to like implement ourselves in the future. Yeah, makes sense. Okay, well, so let's do the calculation. Okay, now it works. Now let's connect this here. Connect this to this source switch and target switch and change the number to 4. See what happens. So I wasn't checking the size of this human. Well, it looks okay. A bit too small, but fine. See what happens. Oh, forgot one thing I should do. I also need to delete these points. Maybe I could well, maybe I could delete the points from here so that I don't need to reconnect everything at each time. Okay. Alright, so recreated the whole mesh again. So more and more mesh you have, more and more detail your meshing will become. Yeah, interesting. Okay, and let's try this out again. I play it. Rubber toy to human head and human head to... Ooh. Cool. So I do see some problem on the leg. It's again due to the precision issue with the triangulation 2D. So that's also something you could fix. Okay, but overall looks fine. Everything is working fine. And that's it. I guess that's it for today's lectures, I think. Let me know if you have any question, feedback, if you have anything in mind, how this could be used or anything. That would be great. And if you have any new ideas, just like last week I got from one of the people in the chat, that would be great. Okay. Well, as always, I am going to upload the files to a GitHub so that you can download and test it on your environment. License-wise, I think I am also able to ship this application if I have notified the license somewhere, maybe on the README on the GitHub. So maybe I would do that as well. If not, if you don't see it, then go to this page and download it for yourself. Yep, that's probably it. Thank you, and hopefully I'll be able to do another Houdini Algorithmic live next week. sometime close to this time. Okay, with different topic. Yeah. Okay, that's it. Hey. Some interesting fashion that I have just made. Nice. Can you show texture morphing preview? Well, texture has to have the same. I mean, texture is applied on the primitive as an attribute, so I don't think it's possible to morph the texture itself in this way, since this is each triangle has a attribute to the shader like this, so you have to create your own shader to change the texture value. So you have to go to the shop or the matte network to create your own shader to change the texture based on the timeline by yourself. If you want to change the texture, if you need to animate the shader, animate the texture. So that's a bit different topic. That's a bit different than UV or position. Right. Any other question? Maybe I should have used this for a thumbnail. This is really cool. Okay. So I guess that's probably it. I am going to end this live, and as soon as I finish the live stream, I'm gonna upload the files to the GitHub and paste the link to the YouTube video description page, and there's also a link to a Windows application, the command line based application for the spherical parameterization on the video description page, so you can download it the file from there. And also I'm going to post the files to a Patreon page of myself, so you could also get from there as well. If you could support me on Patreon, that would also be great. Yeah. Okay, so thank you for joining. See you next week. Good night. Good night.